There is a persistent belief in software engineering that we can write expressive, high-level code and trust the compiler to transform it into a perfectly efficient machine representation. We rely on flags like O3 or link time optimization to fix our abstractions. While modern compilers are marvels of engineering, they operate within a very narrow window of logic. They can fold constants, unroll loops, and inline functions, but they cannot fix a fundamentally broken architectural choice. In this video, we're exploring the optimization wall, the point where the compilers reach ends and your responsibility as a developer begins. We'll look at why algorithmic complexity, memory access patterns, and I/O bottlenecks remain the primary drivers of performance, regardless of how smart your toolchain claims to be. To understand the limits, we must first appreciate the strengths. Compilers excel at micro-optimizations. Take constant folding. If you write it 60 times 60 times 24, the compiler replaces it with 86,400 at compile time. Then there's function inlining, which removes the overhead of a function call by pasting the code directly into the caller. These are local optimizations. The compiler analyzes a small window of code, proves that a change is safe, meaning it won't change the program's behavior, and applies it. However, the safety requirement is a massive constraint. If the compiler cannot prove that an optimization is 100% safe, it must bail out. This is why pointers in languages like C often defeat optimizers. The fear of aliasing forces the compiler to be conservative, leaving performance on the table. Here is the hard truth. No amount of compiler magic can turn an O of n squared algorithm into an O of n log n1. Compilers reduce the constant factor, the time each individual operation takes. They make the n faster, but they cannot change the exponent. If your algorithm requires nested loops over 1 million items, the compiler might make each iteration 20% faster, but the quadratic growth will still crush your performance. Engineers often spend days tweaking compiler flags or writing clever bitwise tricks while ignoring the fact that they are using the wrong data structure. A simple switch from a list to a hash map usually provides a 1000x speedup that no compiler on Earth could ever replicate. Modern CPUs are incredibly fast, but memory is slow. This is known as the memory wall. A CPU can execute hundreds of instructions in the time it takes to fetch a single piece of data from RAM. Compilers try to help with prefetching, but they are limited by your data layout. If your data is scattered across memory, like in a linked list, the CPU spends most of its time waiting. If your data is in a contiguous array, the CPU can stream it efficiently. This cache locality is something the compiler can rarely fix for you. If you design a system based on pointers and disparate objects, you are forcing the hardware to stall. Professional performance engineering is more about managing memory layouts than it is about writing fast code. Finally, we must talk about I/O. In modern cloud applications, your performance is almost never limited by the CPU's ability to crunch numbers. It's limited by the network, the disk, or the database. If your application makes a synchronous network call to a microservice, the CPU might wait for 50 milliseconds. In that time, it could have executed billions of instructions. No compiler optimization can recover that lost time. Saving a few microseconds by optimizing a loop is meaningless if your architecture requires 3 redundant database round trips. We often micro-optimize the parts of the system that are already fast, while ignoring the massive structural delays inherent in our system design. The takeaway isn't that compiler optimizations are useless. They are vital for the baseline performance of our entire industry. The takeaway is that they are the floor, not the ceiling. Stop looking for magic compiler flags to save a slow application. Instead, look at your algorithms, look at your data structures, look at how often you cross the network. True performance is a result of intentional design, not automated tools. Build systems that respect the hardware, and the compiler will handle the rest.